Hello everyone, I am Dr. Lakhvinder Kaur, Associate Professor at Rungta College of Engineering and Technology, Bhilai. Today I am going to explain our topic optical fiber types and characteristics. I hope to share some valuable insights that will benefit you all. So let's get started. These are the content which we are going to discuss in today's lecture: introduction of optical fiber, history and development, structure of optical fiber, how optical fiber works, classification of optical fibers, characteristics of different optical fibers, comparison among different type of optical fibers, applications, and followed by the summary. Introduction to optical fiber. Fiber optic communication is a method of transmitting information from one place to another by sending pulses of light through an optical fiber. The light forms an electromagnetic carrier wave that is modulated to carry information. Optical fiber is a flexible, transparent fiber made by drawing glass, silica or plastic to a diameter slightly thicker than that of a human hair. Also, it enables high speed data transmission, forming the backbone of modern telecommunications. An optical fiber is a dielectric waveguide that operates at optical frequencies. This fiber waveguide is normally cylindrical in form. It confines electromagnetic energy in the form of light to within its surfaces and guides the light in a direction parallel to its axis. History and evolution of optical fiber. Starting with the conceptual beginning, the idea of using light for communication traces back to the late 19th century with early experiments in guiding light through bent glass rods. First optical fiber. In 1970, Corning Glass Works produced the first optical fiber with a loss of 20 dB per kilometer, which was a significant improvement over earlier attempts. Milestone in the field of transmission. By the mid of 1970s, practical optical fiber cables capable of transmitting signals over long distance were developed and deployed. Development in telecommunication field. Throughout the 1980s, optical fiber technology matured and became the standard for telecommunication networks, replacing copper wires due to its superior capacity and reliability. Advancements in transmission. The development of erbium doped fiber amplifiers in the mid of 1980s allowed for long distance transmission without frequent signal regeneration, further boosting the efficiency of fiber optic networks. Widespread adoption. From the year 1990s onwards, fiber optic became important in global telecommunication networks, providing the backbone for internet infrastructure and high speed data transmission. Continued technological advancement. Advances such as wavelength division multiplexing in year 1990 and dense wavelength division multiplexing in the earlys of 2000 dramatically increased the capacity of optical fiber systems, allowing multiple channels of data to be transmitted simultaneously over a single fiber. Research and development. Ongoing research continues to improve fiber optic technology, including the development of new types of fiber such as dispersion shifted and non-zero dispersion shifted fibers and more efficient signal processing techniques. Now, let us consider the structure of an optical fiber. Fiber optic cable consists of 4 parts, namely core, cladding, buffer and the outermost layer as jacket. The core of a fiber cable is a cylinder of plastic that runs all along the fiber cable's length and offers protection by the help of cladding. The diameter of the core depends on the application used. Due to internal reflection, the light travelling within the core reflects the core, the cladding boundary. The core cross section need to be circular one for most of the applications. Cladding is an outer optical material that protects the core. The main function of cladding is that it reflects the light back into the core. When light enters through the core into the cladding, it changes its angle and then reflects back to the core. The main function of the buffer is to protect the fiber from damage, and thousands of optical fibers arranged in hundreds of optical cables. These bundles are protected by the cable's outer covering, which is known as jacket. Fiber optic cables jacket are available in different colors that can easily make us recognize the exact color of the cable we are dealing with. The color yellow clearly signifies a single model cable and color orange indicates the multi-mode. Now, how optical fiber works? The most basic optical fiber consists of a circular cross-section core surrounded by a second material called the cladding, having a lower index of refraction. Light introduced into one end of the fiber at the proper angle will travel through the core and stay contained within it until it emerges out the other end, which is also known as total internal reflection. The phenomena of total internal reflection occurs at the interface between two dielectrices of different refractive indices only when the light is incident on the dielectric of lower index from the dielectric of higher index and the angle of incidence exceeds the critical value. Now, the types of optical fibers. An optical fiber is a piece of very thin and almost absolutely pure glass. It is thin as human hair. Its outside is made of a cladding of glass, which is also another type of glass with slightly different chemical properties and composition. Hence, it has different refractive index compared to inner core material. No single fiber design meet all application requirements, mainly due to many economic reasons. However, manufacturers have concentrated on three broad categories as shown below. This module mainly focuses on the classification of optical fiber and their characteristics. So, let us start with the first type of classification based on refractive index profile. Optical fibers are classified into two types based on the refractive index profile of core and cladding. They are step index fiber and graded index fiber. In step index fiber, core has the constant refractive index N2. At the core cladding interface, there is a sudden decrease in the refractive index from N2 to N1. It remains constant throughout the cladding part of the optical fiber. Hence, the refractive index profile N with reference to the radial distance r from the fiber axis is given as Nr equals to Ni. Now, if r is less than a, then N of r is equals to N1, and if r is greater than equal to a, then N of r is equals to N2, where a is the core radius of optical fiber. Now, this figure shows another type of optical fiber, graded index fiber, in which the refractive index of core N1 decreases gradually from the center of the core as a function of the radius from the center of the optical fiber. At the core cladding interface, the refractive index shows decrease from N1 to N2 and it remains constant with respect to the radial distance r. This type of optical fiber is known as graded index optical fibers. Now, second type of classification is based on the number of modes propagated through optical fiber. Mode is the one which describes the nature of the electromagnetic wave in a waveguide. Optical fiber is considered as cylindrical waveguide and it is the allowed direction whose associated angles satisfy the condition for total internal reflection. Based on the number of modes that propagates through the optical fiber, they are classified as single mode fibers and multi-mode fibers. Now let us discuss both the fibers in detail. Multi-mode or monomode fibers. In a fiber, if only one mode is transmitted through it, then it is said to be a single mode fiber. A typical single mode fiber may have a core radius of 3 micrometer and a numerical aperture of 0.1 at a wavelength of 0.8 micrometer. The condition for the single mode operation is given by the V number of the fiber. V number or normalized frequency is the fundamental relationship between numerical aperture, cutoff wavelength and core radius in step index fibers. By definition, the value of V is equals to 2.405 at the cutoff wavelength of every single mode fiber waveguide. When the value of V value is greater than 2.405, then the fiber will propagate multiple modes. Single mode fiber has following characteristics such as it has only one path of propagation, it has V number less than 2.405, core diameter is very small, no dispersion effect is there, higher bandwidth of approximately 1000 megahertz used for long haul communication, fabrication is difficult and costly. Second type of fiber is multi-mode fibers. If more than one mode is transmitted through optical fiber, then it is said to be multi-mode fiber. The larger core radius of multi-mode fibers make it easier to launch optical power in the fiber and facilitate the end-to-end connection of similar power. Multi-mode optical fibers have following characteristics. It has more than one path, V number is greater than 2.405, the core diameter is higher, it has higher dispersion, it has lower bandwidth of approximately 50 megahertz and it is used for short distance communication. Similarly, the fabrication is less difficult and not costly. Depending on the refractive index profile and the number of modes propagated through the optical fiber, they are further classified into 4 categories. First, step index single mode fiber. Second, step index multi-mode fibers. Third, graded index single mode fiber, and last one, graded index multi-mode fibers. First is step index single mode optical fibers. The core diameter of this type of fiber is very small, that is of the order of wavelength of light to be propagated through the fiber. The refractive index profile has a step change in the refractive index from core to cladding. The main characteristic of step index single mode optical fiber are as follows. It has very small core diameter, due to which it has low numerical aperture, low attenuation and very high bandwidth. Some disadvantages: due to very thin cores create mechanical difficulty in manufacture, handling and splicing of the fiber. Similarly, it is very expensive. Second type of optical fiber is step index multimode optical fiber. Practically, light emanating from any point source will have several paths with different angles of incidence at boundary layer. It may also contain different colors with different frequencies. It is called as step index multimode propagation. Any other light wave which is meeting the core cladding interface at and above the critical value of theta c will also be totally internally reflected, hence will propagate along the core. However, any light wave meeting the core cladding interface at an angle less than theta c will pass into and it will get absorbed by the cladding. Third type of fiber is graded index single mode optical fiber. Graded index optical fiber has a property of gradual variation in refractive index, increasing from the outside of the fiber core to the center of it. The propagation of light through single mode graded index fiber is similar to that for the step index fiber, which was earlier discussed. The light wave travel along the center of the optical fiber. Last and the fourth one is graded index multimode optical fiber. From the figure, it is quite clear that light waves or rays with large angle of incidence travel more path length than those with smaller angles. But we know that the decrease of refractive index allow a higher velocity of light energy propagation. Thus, all waves will reach a given point along the fiber at virtually same time. As a result, the transit time dispersion is reduced. This type of light propagation is referred as graded index multimode propagation through optical fiber. An important note, one important thing to mention here is that in all three types of fiber, namely step index multimode, step index single mode and graded index multimode, the thickness of cladding material around the fiber core should be at least be several wavelengths. This arrangement will prevent light energy losses due to absorption and scattering. Third type of classification of fiber is based on the material used. Optical fibers are made up of materials like silica and plastic. The basic optical material must have the following properties. First, efficient guide for the light waves. Second, low scattering loss. Third, the absorption, attenuation and dispersion of optical energy must be low. Based on the material used for fabrication, they are again classified into two types. First is glass fiber and second is plastic fiber. Plastic fibers. Plastic fibers are manufactured from a polymer performed drawing into a fiber. The losses associated with this type of fiber are about hundreds of dB. They operate at low temperature approximately equal to 125 degrees Celsius, while glass fibers can be used up to 1000 degrees Celsius. These are used in sensors, process control and short distance communication. Some features of plastic fibers are high light gathering capacity, large core area, low cost components, uses visible LEDs, easy to connect or couple. Second type of fiber is glass fiber. The glass fiber are generally fabricated by using mixtures of metal oxides and silica glasses. Silica has a refractive index of 1.458 to 850 nanometers. To produce two similar material having slightly different indices of refraction for the core and cladding, either fluorine or various oxides such as B2O3, GeO2 and P2O3 are added to silica. A fiber with glass core and plastic cladding is called as plastic clad silica or PCS fiber. They have following characteristics like high numerical aperture, large core diameter, high attenuation along with low bandwidth. An advantage of large core is the greater power coupling. The high value of numerical aperture permits use of less expensive surface emitting LEDs. Along with high attenuation and low bandwidth, plastic fibers have poor mechanical strength and low maximum operating temperature. Now let us make comparison of single mode and multi-mode fibers on different parameters. First parameter is core diameter. Single mode fibers are typically 8 to 10 micrometers, whereas multi-mode fibers are typically 50 to 62.5 micrometers. If we consider the light propagation through both the fibers, then in case of single mode fiber, it allows only one mode of light to propagate, whereas multi-mode fiber allows multiple modes of light to propagate. If we compare bandwidth of both the fibers, then single mode fibers has higher bandwidth due to minimal modal dispersion, whereas multi-mode fiber has lower bandwidth due to modal dispersion. If we compare the distance of both the fibers, then single mode fibers are suitable for long distance communication up to hundreds of kilometers or more without amplification, whereas multi-mode fibers are suitable for short distance communication approximately up to 2 kilometers. If we compare the light sources of both the fibers, then single mode fiber uses laser diodes, whereas multi-mode fibers uses light emitting diodes LEDs. Applications: single mode fiber are used in telecommunication, internet and cable TVs, whereas multi-mode fibers are used in local area networks, data centers and short range connections. If we compare the cost of manufacturing of both the fibers, then single mode fibers are more expensive due to precision manufacturing and laser light sources, whereas multi-mode fibers are less expensive and easier to manufacture. If we compare the installation and alignment charges of both the fibers, then single mode fibers require precise alignment due to smaller core size, whereas multi-mode fibers are easier to align due to larger core size. Signal quality: in case of single mode fiber, better signal quality over long distance is available, whereas in multi-mode fiber, more signal degradation over long distance due to modal dispersion is available. Wavelength: if we compare wavelength of both the materials, then single mode fibers operate at 1310 nanometers and 1550 nanometer wavelengths, whereas multi-mode fibers operates at 850 nanometers and 1300 nanometer wavelengths. By comparing these points, you can choose the appropriate type of fiber based on your specific requirements such as distance, bandwidth and cost. Now let us make comparison between the step index and graded index optical fibers. First parameter is refractive index profile. In step index optical fiber, core has a uniform refractive index and there is an abrupt change to a lower refractive index in the cladding. Whereas in graded index optical fiber, the refractive index gradually decreases from the center of the core to the outer edge of the core. Light propagation: in case of step index optical fiber, light rays travel in a zigzag path due to total internal reflection at the core cladding interface. But in case of graded index optical fiber, light rays follows a sinusoidal path, reducing the difference in path length. Next, modal dispersion. In case of step index optical fiber, higher modal dispersion is available due to different path lengths of light rays, leading to pulse broadening. Whereas in case of graded index optical fiber, lower modal dispersion due to gradual refractive index change, leading to less pulse broadening. If we compare the bandwidth of both the fibers, then step index optical fiber has lower bandwidth compared to the graded index fiber due to higher modal dispersion. If we compare the construction of both the fibers, then step index optical fibers are having simple construction with a distinct core and cladding boundary, whereas graded index optical fibers are more complex with a continuously varying refractive index in the core. Applications: step index optical fibers are suitable for short distance communication and applications where high bandwidth is not critical. Graded index optical fibers are suitable for medium to long distance communication and application requiring higher bandwidth. Difference between glass and plastical fibers. Glass fiber optical cables are made from a material called silica, which is very pure and has a very low index of refraction. This means it can carry data over long distances with less signal loss. However, glass is more fragile than plastic and can be difficult to work with. Alternatively, plastic fiber optic cables are made from materials such as acrylate and polyimide. These plastics have a higher index of refraction than glass, meaning they are not suitable for long distance data transmission. However, they are much more flexible than glass and easier to work with. In both cases, additional chemicals may be added during the manufacturing process to improve the performance of the fiber. For example, chemical components like germanium tetrachloride and phosphorus oxychloride may be added to the core fiber or cladding. Difference in cost between the glass and plastic fiber optic cabling. Glass fiber optic cables, these are more expensive to manufacture than plastic ones. This is because the silica used to make them is a lot more costly than the material used for plastic cables. However, glass cables are often seen as a longer term investment due to its durability and data carrying capability. In contrast, plastic fiber optic cables are cheaper to manufacture and easier to work with. However, they are not as durable as glass cables and are not suitable for long distance data transmission. You may also need to factor in the possibility of replacing plastic fiber optic cables periodically. Let us consider different applications of optical fibers. First is communication system. The fiber optic communication system involves the transmission of information from the source to the destination in the form of pulses of infrared light signals. This communication method is suitable for long distance and short distance communication, allowing user to exchange various signals including voice, video, data and telemetry signals. Elements of a fiber optic communication system includes transmitter circuitry, light sources, photodetectors and receiver circuitry. Light emitting diodes or laser lights are preferred sources for transmitting signal in optical fiber communication. In contrast, PN junction diode and avalanche diode are the preferred photodetectors for reception and detection purposes. Fiber communication system is generally preferred over other modes of communication as it proves to be reliable and offer the minimum possibility of the input signal getting affected by electromagnetic interference. Also, The optical fiber based communication system has significantly large bandwidth, fewer chances of signal degradation, provides high data security, is comparatively cost effective and consumes lesser power. Medical equipments. Optical fibers are widely used in various medical equipments and research laboratory machines. For instance, the endoscopic, otoscope, etc. are some diagnostic medical gadgets that rely on optical fibers for their general operation. Optical fibers are usually preferred for medical diagnostic and treatment application because they offer no or minimum side effects and harmful consequences, are flexible, have a significantly lesser surface area and do not emit toxic radiation. Other than diagnostic and treatment application, optical fibers can also be used for research application in the microbiology and biomedical sector. Next important application is Internet. Internet is one of the prominent examples of real life application that makes use of optical fibers. Optical fibers can transmit a large amount of data from one place to another in relatively less time. The high data transmission speed, flexibility, lightweight nature and ability to easily carry bulk data make optical fibers suitable for internet cables in place of traditional copper wires. Next and the most important industry is automotive industry. The automotive industry uses optical fiber to illuminate the interiors of vehicles. This is because optical fiber do not consume much space, radiate bright light, can be deployed flexible in mechanical structure of cars, are economical, do not consume much power, have minimum chances of signal deterioration and leakage, have significantly longer lifespan and do not require frequent maintenance. Next is telephone. The local telephone connectivity within the building, the city or the country and the global telephonic connectivity among users is different in different countries, typically rely on the primarily working principle of optical fibers. The optical fiber cables are bundled together for cellular communication and laid underground or beneath the sea surface area. This increases the security of the signal as the flowing data is less susceptible to electromagnetic interference introduced by other electromagnetic waves in the environment. Next is military application. Data transmitted with the help of fiber optic is highly secure and only authenticated user can access it. Since the main focus of military application is data security and privacy, this unique property of optical fiber can be exploited in many military applications. All the three military applications, namely Army, Navy and aerospace, uses optical fiber to establish a shared channel between the station to exchange information and analyze data. Space application. Some space applications such as satellite communication, remote sensing, high power laser system, multispectral and hyperspectral imaging, optical data communication, atmospheric monitoring and analysis, etc. rely on optical fibers for their operation. Conclusion. Optical fibers are classified based on the refractive index profile of the core, cladding as well as the number of modes travelling through the fiber. Step index fiber and graded index fiber are the types based on the refractive index profile, while single mode fiber and multi-mode fibers are the types based on the number of modes transmitted and propagated through the fiber. There are other types of optical fibers such as depending upon the application in which they are used, like tapered end fibers are used to increase the intensity of dispersed input light. Usefulness of these fibers are compared based on the structure, refractive index profile, immunity to noise, dispersion, etc. Lastly, applications are discussed for military, data link or telephone connections. Thank you.